Hello, this is Navina from Johnson's Institute of Technology. Today we are discussing about calculate the nth Fibonacci sequences using dynamic programming. Dynamic programming is a specialized optimization technique that finds its applications in both mathematics as well as computing. It works on the principle of dividing the problem into smaller subproblems and recursively combining their solutions to obtain the overall solution. Our aim is to simplify a problem by breaking it down recursively till the point we can't divide it any further. Any problem that can be solved by dividing in this manner and using the solution of subproblems built up to the final solution is said to have an optimal substructure. This method was invented by Richard Bellman in the year 1950 and has since then found applications in various fields ranging from engineering, computation to even economics. A very large number of computational algorithms are known to use dynamic programming, and some optimized through the use of the same. In this article, we shall discuss one of the simpler applications and implementations of dynamic programming, which is to find the nth Fibonacci numbers in the series. This method improves heavily on the recursive search by eliminating the need for heavy resources usage of the system stack and slowdown visible especially with large indices. Now we can have a look into the algorithm. Let the index of our required number be n. In order to determine the number in Fibonacci sequence at nth position, we simply follow the premises. F of n is equals to f of n minus 1 plus f of n plus 2. For dynamic programming method, we need to store the previous series somewhere to arrive at the required fn. We make use of an array to perform our task. Length of array is n since we begin index from 0. Now f4 is equals to 0, f1 is equals to 1, and for every position x in the array, fx is equals to fx minus 1 plus fx minus 2. So f2 is equals to f1 plus f0 is equals to 1 plus 0, that is equals to 1, and f3 is equals to f2 plus f1, that is equals to 1 plus 1, that is equals to 2, and so on. Let us see an example for a better idea. Let us take an example of 7th number in the series 0, 1, 1, 2, 3, and so on. Now we have n is equals to 7. In order to find the 7th number, we need to create of an array of length n in order to store the entire series since we begin from 0. We know store every result a sum of values in previous two indices. We get the last number from the array, which is our required result. Thus we divided this problem of the nth number into n subproblems for numbers at every index and used the results of each in order to arrive at our final